So common misconception number 2. And, it's often felt, believed, intuited that objects with high horizontal velocities um, are not pulled down by gravity as hard. Pulled down as hard by gravity. The truth, though, is that the horizontal motion doesn't have anything to do with the acceleration of gravity. The horizontal motion doesn't affect gravity at all. Okay, so here is an example of the kind of thing that people predict wrong. Okay, so imagine that, well, you'd have to be out in a big open space for this to work, but imagine, so you have one person over here with a gun. Ooh, they need to work on their legs a little more. And you have one person, and they need to get their arms shortened. And you have another person over here. And this person drops this bullet at the same instant that this person fires this bullet horizontally. Okay. So this bullet is fired horizontally. Just as a second bullet is dropped. Which one will hit the ground first? Question mark. Okay, so most people's intuition tells them that the bullet's going so fast horizontally that it's not going to fall as fast. And so the bullet basically just keeps going horizontally until it hits something while this bullet falls. And this would hit the ground first. And I think the biggest reason that people tend to have that intuition is because a bullet covers so much ground so fast that you don't tend to ever see it hit you wouldn't see it hit the ground. Normally you would see it hit a wall or something. And if you didn't have walls there, it would be out of your sight and it would take forever to look for it. But the truth is that this follows a parabolic path. It's a pretty shallow parabola because it's covering so much horizontal distance. But if you gave yourself 500 yards or whatever, gave it enough room to hit the ground, what you would see is that 500 yards away, this bullet hits the ground at exactly the same instant that this one hits the ground. So no matter what a projectile is doing, its acceleration is, and we're talking about, something in free fall when I say projectile. So this isn't true of general things that are sitting on a table or being, have other forces acting on them. But if something's in free fall, its acceleration, whether it's going up or down or horizontally or at an angle or whatever, its acceleration is down with a magnitude of g, which is 9.81 meters per second squared. Okay, and so then if your coordinate system is this, then there's the acceleration, okay, pointing down. And then the components of that in this coordinate system are 0, negative g. Okay, if you chose a different coordinate system, it would be different, but it's always down. Okay. Okay, so first I'm going to show this Mythbusters video where they set up this experiment where they hook up some electronics so that a bullet is dropped at the same time it's shot, and then they show that they hit the ground at the same time. It's sort of cool to see. And then we'll see why it works in the calculations.
What you got there?
This is a good one. Picture two bullets, each exactly the same distance from the ground, each released at the exact same second, except one bullet is dropped to the ground, the other is fired from a gun. The classic physics thought experiment states that both bullets will hit the ground at the same time.
Based on what theory?
Based on the theory that the bullet that's fired from the gun has no wings on it, no lift. Thus, gravity has the same effect on it as it does on the drop bullet, and thus, they hit the ground simultaneously.
Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's drop rig, so the boys can take a shot at physics history.
All right, dude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet dropped versus fired. In 3, 2, 1.
But from 360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. Ugh. I can't wait to see the high speed.
Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves and a victory for physics.
Let me put 39.6 milliseconds into some perspective for you. When you go to the movies and watch a projected celluloid film on the screen, you know that that film's made up of individual images, right? What you might not have known is that it takes 24 of those per second to make up the film that you're watching. So each one is on screen for exactly 1/24 of a second, but you don't notice that because it's faster than your eye can register. Well, that 1/24 of a second is actually longer than 39.6 milliseconds. That's how close those two bullets were.
Okay, and if I had to guess, you know, the so they didn't hit at the exact same time, although very, very close to the same time. If I had to guess what the reason was that it, you know, that you saw that tiny little difference in time, it would just be the angle that the gun is at. The tiniest little angle in the gun can make a surprisingly big difference in how long it takes to hit the ground. So we'll talk about that. Yeah.
Also, there could have been a slight delay between the bullet dropping and the bullet firing, and also the bullet while it's in the barrel of the gun doesn't drop.
That's true. Yep. Okay, so let's do an example. And let's say that this bullet is fired horizontally with a speed of 1,000 meters per second, which is probably a little too high, but it's a nice round number. How long does it take for it to hit the ground horizontally? Let me give an initial height of 1 meter. Damn it. Okay, how long does it take to hit the ground? Okay, so what I want you to notice here is that what matters for how long this takes to hit the ground is a y equation for a constant acceleration. And so that means that only y components of things matter. Okay, well, if this is the coordinate system, and this is the velocity at the instant that the bullet's fired, then that velocity is all in the x direction, okay? And so that initial velocity is 1,000, 0. And even though the 1,000 is a really big number, the effect, you know, the component in the y direction is 0, the same as if it's just dropped, okay? So that's what we're gonna see. All right, so let's, Okay, so this height is 1 meter. Yeah, that's true. And it's going to start out with a horizontal velocity, but it's not going to go straight. It's going to go in a very shallow parabola. Okay. I'm going to put the coordinate system on the ground right beneath where the bullet's fired. I'm going to call this instant time equals 0 and this instant time t. And let's think about the variables. So there's t, acceleration vector, initial position, position at time t, initial velocity, and velocity at time t. Time is what we're trying to calculate. We don't know it yet. Acceleration is straight down, so that's going to be in the negative y direction with our coordinate system. The initial position, that's the coordinates of the bullet at time equals 0. So that's 0 for x, 1 for y. The position at time t, we don't know the x component of the position. We don't know the x coordinate of the thing at time t, but we do know that the y coordinate is 0. Initial velocity, I showed that above, that's 1,000, 0. And then we don't know velocity at time t. So is there an equation that we can use with these that has t in it and everything else in it is listed here? And the equation that's going to work is py is equal to p0y plus v0y t plus 1/2 ay t squared. And so this equation says 0 is equal to 1 plus 0 times time minus 4.905 t squared. And if you calculate that, I think you get a time of 0.452. Well, you do it with a square root, you get plus or minus, and we want the positive times. So look at this equation, though, and notice that what would happen with this calculation if there was no 1,000 meters per second in the x direction? If it was just dropped straight down, we could do this as a one-dimensional problem, right? Call our positive direction up. And this equation would just be the one-dimensional constant acceleration equation for position. And you would have these exact same numbers in it. So according to the math, whether it's 1,000 or 1,000,000 or 200 or whatever, it just doesn't even show up in determining how long it'll take to hit the ground. It would make a difference in how far away it hits the ground, but that wasn't what we were calculating here. Any questions about that? Okay, well, let's do a similar example. But let's say that this time the gun is fired at an angle. So if this is the horizontal, let's say it's fired a little bit below horizontal. And let's say that this, I think this is probably still exaggerated for what, come on, for what I'm going to say this is, but let's say that this angle is 0.5 degrees below the horizontal. Okay, 0.5 degrees is a tiny angle. But what we're going to see is that it makes a very significant difference in how long it takes to hit the ground. So it's still fired at 1,000 meters per second from 1 meter high. But this time it's 0.5 degrees below the horizontal. How long does it take to hit the ground? Okay, so let's use all the same stuff we did before. Ooh, that guy has forehead problems. So again, I'm going to choose the coordinate system to be on the ground right below where it's fired with the y-axis up and the x-axis horizontal. And this distance is going to be 1 meter again. And this is going to be the time equals 0 instant. This is going to be the time t instant. And let's figure out what variables we know and what we want to calculate. Okay, well, we're trying to calculate time again. Again, we know the acceleration. In this coordinate system, it's 0, negative 9.81. P0 is the same as it was, 0, 1. We know Py is equal to 0. We don't know Px. And now for the initial velocity, I'll calculate it over here. Here's our coordinate system. The vector is like this. Where this angle is 0.5 degrees. And so that means that V0 is 1,000 times cosine of negative 0.5, 1,000 sine of negative 0.5. I think I got it here. So we have, so tell me if this is right, 999.96 for the x component. And then for the y component, negative 8.73. And then we don't know v. Well, again, we're keeping it to ourselves that we know that the x component is going to stay that for any time. And so we're going to use the same equation that we did for the last example. So py is equal to p0y plus v0y t plus 1/2 ay t squared. So 0 is equal to 1 minus 8.73 t minus 4.905 t squared. And you can do this with the quadratic formula. So here's your a, here's your b and c. Can someone calculate this and tell me what the answers are? So t, we're going to get 2 roots for this.
I got negative 1.89
Okay.
and 0.108.
108. Okay. We don't want negative times, so it's this one. So having the muzzle of this gun misaligned by 1/2 degree, which is a really tiny angle, changed the amount of time it took for this to hit the ground from 0.452 seconds to 0.108 seconds. Okay, it took 1/4 of the time. But if you think of this as a one-dimensional, so you can always think of the components of these equations as one-dimensional problems. Okay, and so look at what this would be as a one-dimensional problem, and it'll help you make sense out of that huge change in the amount of time it takes to hit the ground. The equivalent in one dimension to this is something that started at a height of 1 meter and was initially thrown down towards the ground at 8.73 meters per second. So like about 20 miles an hour from a meter in the air. Okay. And if you did that problem, you know, it looks just like this, you get the same answer. Well, of course, it's going to take a lot less time if you throw something down toward the ground at 20 miles an hour. So the reason that that y component is so big is that even though 0.5 degrees is a tiny angle and sine of 0.5 degrees is a tiny number, if you're multiplying it by something as big as 1,000, it's going to end up as a pretty significant contribution. Okay. So, like, would it make that much of a difference if you were 1/2 degree misaligned with something that was launched at 10 meters per second? No, not at all. It wouldn't be anywhere. It wouldn't be anywhere near as much.